Okay, I think we are now ready to start the fourth session of the bi-level optimization webinar. Thank you all for coming today. And okay, we have two speakers today. The first one is by Bolin. Um, Bolin is an incoming assistant professor at the National University of Singapore. His research focus on AI for sustainable cities. He develops machine learning and optimization technique to evaluate, design, and help people interact with urban systems. And also, he's interested in integration of machine learning and optimization, aiming to improve the efficiency, effectiveness, and applicability of data-driven decision-making tools. His research has been recognized by several awards, including Inform's George Danzig Dissertation Award, Inform's Daniel Wagner Prize, Inform's TSL Best Student Paper Award, among many others. In 2023, he interned at Uber as an applied scientist. Thank you for inviting our invitations, Bo, and the floor is yours.
Thank you. Yeah, let me share my screen. Can you see my screen now?
Yes.
Okay, great. Yeah, thank you, Nagisa, for the very nice introduction and also for the invitation. I think this is such a nice opportunity for the community to get together, talk about fun ideas, and also, especially for junior people like myself, to demonstrate our work. So I definitely appreciate that. And also, thanks everybody for coming. My name is Bo. I'll be joining the National University of Singapore very soon, actually just next month. I'm very excited to share with you this paper that I wrote during my PhD with my advisor, Tim Chen from Toronto, and also Professor Eric Delage, who I visited in Montreal back to 2023. Okay, so the overarching goal of this paper is we want to develop some algorithms that can make decision recommendations that are more likely to be adopted by human beings. Okay, and as you can probably guess based on the title, I'm going to use some technique called inverse optimization, which I think is a special case of bi-level programming. So think of this as a application of bi-level optimization in the context of human AI interaction. Okay. So yeah, before I get into the technical details, let me start with some like practical motivation of this work. Okay, so the paper was actually motivated by some observations we had on the ride-sharing platforms. Okay, so we know that ride-share drivers, they don't always follow the path recommendations that they are given. So for me personally, I didn't really think that's a very big issue at the very beginning because, you know, like drivers, they usually know the city very well and maybe they can find a better path. And usually I'm willing to follow that. However, I did an internship several years ago at Uber, and I was chatting with my data scientist friends there. They told me that this kind of deviation is actually undesirable from an operational perspective, and there are two reasons. Reason number one, this is going to affect rider experience. It's for sure going to cause confusions for the riders and sometimes even safety concerns. Imagine that you take an Uber home at midnight, your driver suddenly deviates into a very sketchy neighborhood, and he may tell you that, oh, I'm taking a shortcut. But I mean, still, it could be scary, at least for some people. And the second reason here is that it's going to affect the efficiency of many downstream problems, right? So there are hundreds of data scientists working very hard, trying to estimate the arrival time, price the trip, and do many other things, assuming that the driver will follow the recommendation because this recommended path is an important input to all these algorithms, and they have to decide this even before the driver accepts the invitation. And if the driver chooses to deviate, then it just messes up everything. Okay? So I became interested in this problem because of all these discussions, and then I did a bit more research online. And what I found here is that this is actually a very common phenomenon that has been documented in a variety of contexts. Okay, so we have seen this. And in the literature, people call this algorithm aversion, meaning that algorithms are getting better and better these days, but we human beings are still reluctant to adopt these recommendations for different reasons. So we have seen this in ride sharing, in last mile delivery in a very similar way. And just as one more example to show you that this can be costly. Okay, so in this retail operations paper, the author actually did a field experiments where they use some data-driven tools to provide like inventory recommendations for some managers of offline retail stores. And they found that these recommendations were actually overridden very often, over half of the time in practice, leading to an almost 6% reduction in profits. Okay, so this can indeed lead to some non-trivial economic loss. A very natural question based on all this example is that if algorithms are so good, why are people averse to them? Right? So there's a growing body of empirical research on this topic. People have identified many different reasons. I'm not going to read the list, and this is by no means comprehensive, but I do think it's an important research question because once we understand all these reasons, we can start thinking about what levers we can apply to mitigate algorithm aversion. And this is what we're going to do in today's presentation. Okay, we're going to focus on the first reason, the misalignments between algorithms and human intuition. And this is particularly relevant in many transportation problems that involves routing, because drivers usually deviate because they don't believe the given path is good. They think they have a better idea. Right? So essentially, the research question we're asking here is like, how do we generate a decision that is not only high quality, but also perceived as high quality by humans, so they're more likely to be adopted? Okay. And the key challenge here is like, how do we even quantify human perception? If you ask a driver to tell us about her intuition of a road network, most likely the response is, I don't know, because it's not something we can easily communicate and articulate to each other. Right? So instead, I'm going to look at how people made decisions in the past, and hopefully we can learn something useful from those historical data that can inform our future recommendation. Okay. With that, let me formally set up the problem for you. Okay, so in this paper, we assume that when making a decision, people solve an optimization problem in their mind. And I'm going to call this a forward problem because later I'll define another problem called inverse problem. And throughout the presentation, I'll use the shortest path problem as an example, but the method is actually general. The only assumption we need here is the problem is linear. Okay. So imagine that this is the road network in the city that you live in. I'm going to talk about Toronto because this is where I am right now. Okay, so for each of us, we have a feasible region that corresponds to the set of all possible paths going from one origin to one destination on this network. Okay, so that's the feasible region. And in the objective function, we have some parameter, theta. So think of this as the travel time on each road segment in the city. And I'm trying to minimize the total travel time along the routes. Right. In reality, people usually don't have access to precise travel time. So people drive based on their own intuition, denoted by theta hat. Right? And we solve the problem. We get a decision, x hat, which is the path from O to D. In practice, it's very difficult to read people's mind. So we never really observe human intuition. But especially for those platforms like Uber, Lyft, it's very easy for them to see the feasible region corresponding to the origin and destination of a trip, and also the final path taken by the driver. And of course, Toronto is a very big city, so potentially we can access many this kind of feasible region and decision pairs from different drivers from different trips. And using this kind of data, our goal today is we want to derive a decision policy pie. Okay, so in the future, when I see a new feasible region or a new origin destination pair, I can use this policy to give a recommendation. Okay, so to get a good decision policy, the first order question we have to answer is how do we even evaluate these different policies, right? And for this, I'm going to propose two evaluation metrics, one objective and one subjective. The first metric is called actual optimality gap. Okay, so we assume that there are some ground truth cost vector, theta star. Think of this as the real travel time on each road segment. Based on theta star, whenever we get a recommendation, pi x, we can calculate the optimality gap of my recommendation on the forward problem. Okay? And we take expectation over the random feasible region because origin destination pairs can randomly pop up in the city. And we focus on the case where we use one policy to give recommendation to everybody. Okay? So that's the first one. The second metric is called perceived optimality gap, or POG. Okay, so the formula looks very similar. The only difference here is instead of using the ground truth information, which most people don't have access to, we rely on human intuition denoted by theta hat to calculate this optimality gap. Okay. And again, we take expectation over random feasible region and also random human perception this time. So this is also a random variable. So conceptually, think of AOG as a measure of how good my recommendation actually is, and POG as a measure of how good people think my recommendation is. And our goal is to find a pi that has low AOG, low POG simultaneously, meaning that the recommendations are great and people believe in us. Okay. So how do we do this? In the literature, there's a very natural idea called estimate and optimize. Okay. So the idea being, by leveraging this kind of decision data, maybe we can first try to get a point estimate of those parameter theta in the objective function that we don't know. Right? And this actually turns out to be a difficult problem because we're trying to estimate something that we never really observe. Right? But luckily in the literature, there's a method called inverse optimization that allows us to do this kind of estimation. So for those who are not very familiar with the concept, here's a very brief introduction. So inverse optimization 101. Okay, so essentially I'm going to solve a bi-level optimization problem called inverse problem, where the decision variables include theta, which is the cost vector that I'm trying to estimate. Right? And this is an empirical risk minimization problem. So I'm trying to minimize the empirical risk over my data set. Each data point is one historical decision. Okay, so for each data point I, the loss is defined as the suboptimality of the decision I observe, x hat, under my theta. Okay, so if I can find a theta that really make my historical decision optimal to the forward problem, then this loss will be zero. Okay, so think of this as the opposite process of the forward optimization, right? So in forward optimization, people know what they're thinking about. They solve the problem to find a decision. But in this inverse process, we see what they did and we try to reverse engineer what they were thinking about. Right? And we do so by looking for one theta that can rationalize people's historical decision as much as possible. Okay. So that's the idea. This is only one way to formulate the inverse problem. There are different variants in the literature, but the point here is that this has been done, and there are ways to get this kind of point estimate. Okay, and once we have the estimate, in the future, when we see a new feasible region, we can simply just solve the forward problem to derive a recommendation. Okay, so this is a straightforward idea. It's been done many times in the literature, but as I'll show you later, this is not going to perform very well in our setting. The challenge here is that, in traditional inverse optimization setting, an implicit assumption that people make is that all the individuals who contribute to the data set have very similar perception. So they think very similarly. So it makes sense to use a point estimate to represent everybody. But in many practical problems, people can think quite differently, right? So when it comes to driving, for example, my driving preference can be very different from yours. There's potentially a very wide distribution. And in this case, it doesn't make sense to use one point estimate because there's essentially no consensus in my data set. Right? And when we apply this point estimate to a specific individual, there's likely non-trivial estimation error. And we know that we're dealing with a linear problem. So the optimal solution is actually very sensitive even to small changes to the cost vector. So estimation error can be significantly amplified in the second stage when we make a recommendation. So following this intuition, we're able to show that if we use this kind of traditional pipeline in our setting, then we can have arbitrarily large AOG and POG simultaneously, meaning that the recommendations can be bad and people don't believe in us. So how do we do better? Here's our proposal. Okay, so we have this new pipeline. The key difference here is instead of getting a point estimate in the first step, now I'm going to try to construct an uncertainty set for those unknown parameters. Right? And I'll try to make sure that this uncertainty set contains a future decision maker's perception with high probability, gamma. Okay, and then based on this uncertainty set, in the future, when I see a new feasible region, I'm going to solve this robust model to recommend a decision. Okay? And hopefully people will like most people will like my recommendation because their perceptions have already been captured by this uncertainty set. Okay, so following this intuition, by doing some theoretical analysis, which I won't get into in today's presentation, we can have some upper bounded AOG and POG simultaneously when using this pipeline, meaning that the recommendations are good and people will believe in us. Okay. So all is fine, but then in order to make this new pipeline work, the problem we have to figure out is how do we go from decision data to this uncertainty sets? And this has actually never been done in the literature. Right, so in the robust optimization community, there's a huge literature on how to construct uncertainty set using data. Right? But unfortunately, those methods are not applicable in our problem because they require observations of the unknown parameters. But unknown parameters represent human intuition in our problem, which we never really observe, so we cannot use those approaches. What we observe are some decisions that people made based on those unknown parameters. So there's an additional layer of complexity, and that's the challenge we have to deal with. Okay. So we have this new methodology that allows us to construct uncertainty set only using decision data. The method has 3 steps. Step number 1, I'm going to split the data into 2 parts. Okay, so training, validation. Right. So for the training parts, I'm going to apply the traditional inverse optimization method to get a point estimate. And then I'll use this validation data set to calibrate an uncertainty set around the point estimate. And hopefully this uncertainty set have some performance guarantees. Okay, so the key innovation here is in this final step, and this will be the focus for the rest of this talk. Okay. Okay, so before I define the uncertainty sets, let me remind you about the facts that we're dealing with a linear optimization problem. Okay, there could be some integer like decisions, but the function needs to be linear. Okay, and because of this structure, we know that the scale of theta doesn't really affect the optimal solution to the forward problem. So if we multiply theta by a positive constant, the optimal solution wouldn't change. Because of this, without loss of generality, I can assume that all the possible theta have fixed L2 norm. Okay, so in this 2D example, all of them are pointing to the sphere of this unit ball. Okay. So given the point estimate I get from the previous step, we can now simply define the uncertainty set as the set of cost vectors that are within alpha angle of this point estimate. Okay. And this alpha basically control the size of my uncertainty set, and this is the parameter that we have to calibrate using my validation data. Okay. So again, I'm going to formalize the calibration process as an optimization problem. Okay, so here, the decision variables, of course, include alpha, which is what we are trying to decide. We also model the perceptions of each individual who contribute to my validation data set, denoted by theta I, and the norm is fixed to 1 because of this observation. Okay. And we have two constraints. Number one, this is just the definition of human perception. The perception of person I should make her decision optimal to the corresponding forward problem, and this can be represented using some optimality conditions. We have a second constraint here, basically saying that the uncertainty set needs to be large enough so it contains some cost vectors that can rationalize a fraction of the decisions we observe in the validation data set. Okay, so think of this gamma as a hyperparameter, for example, 90 or 95%. Okay. And the goal of this model is to minimize the size of the uncertainty set. Okay, so you probably have noticed already that we can trivially satisfy this second constraint just by setting alpha to pi, right? So the set is very large. We can rationalize everybody's decision, but this is not going to be very useful in the recommendation process because this is too conservative, right? So that's why we're trying to minimize the size. And furthermore, in the paper, we were able to show that the calibration problem can be solved efficiently using some decomposition ideas, and the set will still be valid out of sample. Okay. So yeah, very high-level summary. Happy to talk more later, but now let me show you some numerical results. Okay, so we use this approach to provide path recommendations to delivery couriers around the University of Toronto campus. I want to emphasize here that this is a semi-simulated case study. So the network's real, the locations are real, but the human perceptions and the routes, they are simulated. Okay. So what's going on here is we play the role of a delivery platform. We give recommendation to the couriers who are trying to solve some multi-objective shortest path problem. So they're trying to balance travel time, travel distance, and so on and so forth. The weight, theta, that the courier assigned to different objectives reflects her routing preferences. Right? And these are the parameters that we have to estimate. And these are sampled from some behavioral model that people fit in the literature. Okay. So if my recommendation has a POG that is within either percent from the perceived optimality, then she's going to follow the recommendation. Otherwise, she will deviate. Okay, so eta here really reflects people's tolerance for suboptimal recommendation. Right? If this is very small, then this is a very proud courier who doesn't listen to any advice. But if eta is very large, then this is a humble courier who are kind of more open to other people's suggestions. We care about two outcomes. Adherence rate, this is important for operational efficiency, as I mentioned earlier, and also delivery time. This is important for service quality. Okay, so first of all, this is what happened if we simply just recommend the shortest path, which I believe is the industry practice right now. We see that as people's tolerance increases, adherence rate goes up. This is expected. And at the same time, delivery time goes down because they're more and more likely to just take the shortest path. Okay. If we use our approach, we can clearly see that we can improve the adherence by quite a lot, right? So we go from 20% to 80% in the first case, for example, especially for those very proud couriers. Quite surprisingly, the delivery time also goes down. Right? I said this is surprising because by definition, my path should be longer than the shortest path. Right? So what's happening here is, although my path is slightly longer than the shortest path, they're still much shorter than what human would figure out if they were to optimize for their preference to the extreme. right? So the improvements in adherence can be translated into a decreases in delivery time as well, and we have a win-win in this regime. On the other hand, if we have some humble couriers who are going to accept the shortest path recommendations anyways, then there's going to be a trade-off, right? So we can still improve adherence rates, but this time we're going to incur higher delivery time. Okay. And finally, compared to traditional inverse method, we have kind of similar adherence rates, but we consistently have lower delivery time, meaning that we can provide a better trade-off between these two outcomes. Okay, I think we're almost at time, so let me just quickly wrap up. Okay, I think the most important message I want to get through today is I think it's important to consider human behavior when we design algorithms. I mean, no matter how fancy our algorithms are, if people don't adopt them in practice, then it's not very useful. Right? And personally, this is my first attempt along this direction. We have something that combine inverse and robust optimization to improve the alignments of my recommendation. What I didn't have time to talk about today is, first of all, computational efficiency. Right? We have to solve many optimization problems in this process, and we have algorithm to accelerate the process. There are also some empirical insights into the choice of hyperparameters and also the model performance in different scenarios. So if you're interested, please check our paper online, and we always welcome feedback, questions, and I'll stop here. Thank you.